Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today, as promised in the video last week, I just wanted to very quickly talk about a couple of examples about how we can reformulate problems to be amenable to solution by linear least squares. And we're going to do that by looking at, first of all, fitting a plane to a set of points in 3 dimensions, which is actually an example of multilinear regression, which another possibly quite interesting topic, one I'm not going to go into specifically, except to talk about it just in this example. And then also I want to talk about fitting a circle to a set of points in 2 dimensions, with the caveat, of course, that this linear least squares is really not the best way of doing that, but it does work, and it does at least show a very interesting example about how we can approach reformulating problems to be amenable to solution by linear least squares. Anyway, I hope that will be of interest. So I don't like to do long introductions, so just quickly to say before we dive into that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make videos roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, without much further ado, let's jump to it and let's look at a couple of examples about how we can reformulate problems to be solvable using linear least squares. So, in the last video we looked at linear least squares, including how to derive the equation behind the process. We then went on to look at how we could implement this into the linear algebra library, and we looked at how it could be used to perform simple linear regression to find the line of best fit through some data points. In this video, I want to take that a bit further by showing 2 examples that demonstrate how different sorts of problems can be reformulated in such a way as to make it possible to solve them by applying the linear least squares code that we developed last week. In particular, I'm going to show examples of fitting a 3D plane to a point cloud and of fitting a circle in 2 dimensions. Let's recap what we saw in the last video. We derived this equation for the process of linear least squares and observed how this is similar to the x minus a to the minus 1b form that we had at the beginning when we first started looking at systems of linear equations. In that case, we couldn't handle systems with more equations than unknowns because the matrix of coefficients was not square. The linear least squares equation effectively takes care of this by computing x transpose times x, which will always be square with dimensions of k by k for a system with k unknowns. As this matrix is square, we can compute the inverse, and so we can solve the system, or at least find the best approximation of a solution. We then went on to show how we could use this method to find the line of best fit through some data. This is the classic linear regression situation that I'm sure will be familiar to most of you. So today I want to look at a couple of more interesting examples. We will look at fitting a 3D plane and a 2D circle to some random data. Let's look at fitting a plane first. This case is actually an example of multilinear regression, where we have multiple independent variables and a single dependent variable, as shown here for n observations of m variables. We know that the general equation for a plane is given by this equation. This appears to have 4 unknowns, a, b, c, and d, which would require a system of 4 equations, or 4 observations, to be able to find a solution. But we know that a plane can be uniquely defined by just 3 points, observations. So what is going on here? We can see what is happening if we rearrange the general plane equation so that it is in terms of z. We can do that as shown here, which gives us the result here in the middle. Or, if we arrange that like this, we see that we do actually have only 3 unknowns. This matches what we would expect intuitively from the form of a plane. So, we can express our unknowns now in the form of a vector, beta, like this. And then we can write the whole system of equations in the appropriate form for solution by linear least squares. And we can see that this is in the form of y equals x beta, and we know from the previous video how we can go about solving this, or at least finding the best approximation of a solution beta hat. This is a simple example for the plane given by z equals x plus y, with 100 points that were defined to be on that plane at random x, y locations, and then randomly shifted in z. The points are shown in purple, the fitted plane in turquoise, and we can easily see that the plane is indeed the plane of best fit to these points. Actually, we can see this more clearly if we plot everything properly in 3D, as shown in this animation. Okay, so let's consider our second example of fitting a circle. The first thing to mention, and it is really important, is that this is not the best way for fitting a circle to a set of points in the general case. Under the right conditions, when the points to which we are fitting are roughly aligned with the circle to begin with, this method works very well. Despite this, it does provide a very nice example of using linear least squares, and I will go on to show an example where the method works very well and one where it doesn't. As we did for the plane, we begin with the general equation for a circle, as we see here. Now in this case, although we can rearrange this to be in terms of y, doing so doesn't really help with getting it into a form suitable for linear least squares. Instead, we can rearrange it like this, to be in terms of x squared plus y squared, as shown. Now, we can see that this can be quite easily expressed in a form suitable for linear least squares. And, of course, we can now solve for beta hat, as before. But doing so will give us the values for a, b, and c in the original equation. But how do we go from those to an actual circle in terms of the location of the centre point and the radius? Well, we can rearrange the general equation for a circle by completing the square to give this, which is in the form of x minus u all squared plus y minus v all squared equals r squared, where u and v are the location of the centre point and r is the radius. From this, we can see that u, v, and r will be given by the following. In this example, I have produced 100 points that deviate randomly from a circle with a centre location of 10,5 and a radius of 3. The random points are shown in purple and the fitted circle in turquoise. So, why did I say that this wasn't a good approach? Well, it turns out that this method is very sensitive to outliers in the data. This is because every point is weighted equally. If the points in question are already quite closely aligned to a circle, then this isn't a problem. But in the more general case, we would probably want to consider another approach, such as non-linear least squares with an iterative solution. Let's have a quick look at what happens if we introduce just one outlier point to the same situation we had before. So, here we have just one outlier point out of 100, a location at the origin, 0, 0, and as you can see, the effect of just one point being significantly out of place is considerable, and this is no longer a good fit to the data at all. So, it is really important to keep that in mind. I might do a video in the future looking at other methods for fitting circles, but that isn't something I'm planning to do right now. I think for now, though, that this provides a good example of how linear least squares can be used to solve a variety of problems. The trick is to find a way to restate the problem in the right form and rearrange the equations accordingly. Okay, so let's have a look at some code that implements these ideas. Okay, so if we take a look at the code that I've put together, what I've done is created two separate CPP files, one for testing the fitting of a plane in the three-dimensional case, and a separate one for testing fitting a circle to the two-dimensional points that we've just seen. So just want to have a look through how I've gone about doing that, and I think it provides really quite a nice example about how different problems can be formulated into such a way as to make them amenable to solution by linear least squares, subject of course to the caveats that I mentioned just now. So to start with, we have the usual bunch of stuff that we include. There's probably a bit more there than we really need, but I think as I've been developing these files, I've included various things and then I've copied and pasted that code, so it may have got a bit bloated, but that's okay. We of course bring in qbmatrix.h, qbvector.h. I've talked about this path. I will soon be putting all of this together into a library and hopefully making that available up on GitHub, and of course in that case then everything will be in the same path, which would be much better, but I'll make a separate announcement about that obviously at the time. And of course we bring in qblsq.h, and as always with my testing code I do use using namespace std. This is really not recommended. Lots of people out there make YouTube videos saying why this is a bad thing, and they're absolutely right. However, for this kind of test code I think really it's okay, because I'm using quite a lot of couts and things. I to be honest, I really think it's okay. So to start with then, I have a simple function to write points out to a CSV file. That's because obviously we're working in 3 dimensions here, and it's one thing to display the results that we get back for the the solution to beta hat, but it's another thing actually to be able to visualize what's really happening, and in order to do that it's necessary to write the data out to a CSV file, and then of course you can plot that using whatever your favorite data plotting tool might be. I dare say you could do it with Excel. I haven't tried. I do my plots using GNU Plot, which I think is excellent, and that works really well, but you can obviously read anything that can read a CSV file. It would work. So of course we have template class T, void write to file, and we accept as input points x, points y, and points z. Obviously this is 3 dimensions, so we have x, y, and z. All of those are const std : vector of type T, and then we have a single here const std string file name for the file name. Now I've used std : here because I've using namespace std. I didn't really need to do that actually, but that's just my habit, which I think is a good habit to get into. Anyway, we declare a file stream called original points. We do original points.open file name, and we're not checking to see if that was successful or anything. We should do that, but I haven't really, for the sake of brevity. So then we simply loop through all of the points in points x. We assume x, y, and z are all the same size. Again, something else that if you were being really thorough, we should check, but again, I think it's all right. And then we simply output points x, points y, and points z into original points using this notation here, and then close the file. So that's really very simple indeed. We then have a function to print a matrix to std out. I've talked about that before, as I've talked about the function to print a vector as well, so I won't talk about those now. And we then come into int main, the entry point for the code, and the first thing we set up a random number generator. So this is something that I've talked about before. How we do random numbers. We're keeping everything uniform, obviously real. We have 2 distributions, one for x, y, and one for z. So the way I've approached doing this is to create a set of 100 points, although you can change that, which are distributed randomly, uniformly and randomly across x and y, and then I give them a random displacement in z. So we'll see in a moment how that works. So anyway, the first testing the basic plane. We display to the user what we're going to do, and then we form a suitable set of random points. So we set up vector std vector objects of type double for points x, points y, and points z. Define num points as 100. I've just defined the plane in terms of a, b, and c fitting into this equation. So if ax plus by plus c equals z, you can reconfigure that however you like. It's not too important. So this is a bit I was talking about. We loop over all of the num points, and then we calculate x and y. We simply get those from our distribution, so they're simply random. And then we calculate the value of z according to the equation that we want for our plane. And of course, that would put all of the points exactly on the plane, which is not what we want. We want to find the plane of best fit. So when we then go about storing the data, we push back x, push back y, and when we come to push back z, we add a random number from the z distribution, so we get a random displacement between -1 and 1, and that will give us a random set of 100, or a set of 100 randomly positioned points in 3 dimensions that are broadly all centered on the plane given by z equals x plus y. Okay, and then I've simply got this call to that function to write to file that up at the top, which writes out points x, points y, and points z, so that we have the original points. Writes them out to, well, I've just used that file name and path. Obviously you can use whatever you like. And then we go about actually the interesting part, which is implementing linear least squares. So first off, we need to arrange the data for the problem. Okay, so we define first of all a QB vector of type double object for y, of size num points. We then set up our matrix for x, which is QB matrix 2 of type double, which is of size num points by 3, because we have 3 columns in the matrix, as we just saw in the slide, and num points rows. And then we define the vector for beta hat, QB vector type double, of size 3. And then we're going to loop through all of the points, and we're going to assemble our data into the right format. So we simply do y.setElement at I to point z at I. Okay, so y is simply going to be all of the z values, and then the first column in x we set to the x values, the second column in x we set to the y values, and the third column in x we set to 1, exactly as we saw in the slides. And then we can simply use the QBLSQ function as we've seen before, just this, literally just that, to compute an approximate solution for beta hat, and then we display that out using print vector. So what we can do if we run that code now, what we should find is that we get values out of beta hat that are at least close to 1, 1, and 0. So let's have a look at that now. Let's switch to our terminal window. Here we go. And we're going to compile the code first. So g++ -o test code underscore qblsq underscore plain. And the file we want is called qblsq test code underscore qblsq plain.cpp. We do -std equals c++17. Let's just run that. Okay, and then we can run our code, test code qblsq plain. Okay, and that's really all it does. It just says testing with the basic plane. The raw result of linear least squares is 0.98, 0.853, and -0.136, which is relatively close to 1, 1, and 0. If we run it again multiple times, we can see we do get different values, of course, because our random distribution is changing, so we can do it a few times like that. And we see that in all cases it's relatively close to the values that we want. Of course, it's not exact because it's an approximation, and it's the plane of best fit to the data that we've got, which is very unlikely to be exactly the plane that we started with. Okay, so there we go. That's everything to do with fitting a plane. Let's have a look at the code to do the circle problem. Okay, so looking at the code that we have for fitting a circle, a great deal of this is exactly the same as the code as we had before, so I'm not really going to talk about that. The one thing that I've added here is a simple function to generate points around a circle, which is new and simply saves time. This accepts as input values of cx, cy, and r as constant type t, and a number of points defining how many points we want around the circle. And then we have references to points x and points y, both of type std vector, into which we're going to put the output. We then resize the vectors for the output, so points x dot resize num points and points y dot resize num points to make sure that those are indeed the right size. And then we're going to compute theta step. Obviously we're going to create a circle. We're going to loop theta, the angle, from 0 through to pi by 2, or pi by 2 minus 1 step. So we calculate current theta is set initially to 0. We're dealing with templates, so we have it as type t. So we need to static cast 0 to type t, and then we can define theta step as simply being 2 pi divided by num points minus 1. The minus 1 is important because we don't need to go to 360, because obviously 0 and 360 degrees are the same, so we don't need to do that. Okay, we then simply generate the output by looping I from 0 to num points. That's very straightforward, and then we simply do points x at I is equal to cx plus r times cos theta, and points y at I is equal to cy plus r times sine theta. And then, of course, we remember that we need to increment theta. And that's it, really, very straightforward. That will create the points around a circle. And we then have our function to write the points out to a CSV file. That's exactly as we saw before, except, of course, it only accepts x and y, doesn't need z. We then have functions for printing vectors and matrices that we've seen before. So then we come to in main, the entry point for our code. We define our random number distributions. We have two different distributions this time, one for theta and one for rho. The theta distribution for angles runs from 0 to 2 pi, so this is for the set of points that we're going to generate around our circle. So obviously we want to run from 0 to 2 pi, and yep, just like that. And then we have our rho distribution, the rho or the radius, we set to -0.5 and 0.5, so that will be a displacement from the actual radius. And then we did test 1, testing with a basic circle. we generate the points randomly distributed around the circle. We define Cx and Cy as 10 and 5 and the radius of 3. That's the same example that we saw in the slides just now. We define num points as 100, set up STD vector objects of points x and points y, and then we're going to simply loop through and populate those. Now I haven't used the generate points circle function because we're doing random distributions. So we set theta equal to the theta distribution, and then we set r, new r, equal to the original radius plus a random number drawn from the row distribution, so that we'll get points that are aligned, that are around the circle, and then we simply push those back into x and y, have Cx plus new r times cos theta and Cy plus new r times sine theta, and we use the write to file function to write those out. Of course, as I just mentioned, this version of write to file accepts only two inputs for points x and points y because we've only got 2 dimensions, so they are kind of function specific, so do bear that in mind. It's not quite the same as the example for the plane class. We then set up our problem to be amenable to solution with linear least squares. So the first thing we do, define a QB vector type double for y, QB matrix 2 of type double for x, which has num points, rows, and 3 columns, the same size as for the plane. And then we define a QB vector object for beta hat, and then we're going to populate with our data. We do y.set element I, and notice this is different to the plane example where we just had z going into y. Now we have points x times points x plus points y times points y, the same points x squared plus y squared as we saw in the slides. And then we set the first column of x to points x, the second column to points y, and the third column to 1. Note the minus signs here are important because if you look back on the slide, we had the minus sign there, which is very important to get that right. And that's all we need to do. We can then put those into the QBLSQ function as shown there, and that should give us our solution for beta hat. And of course beta hat will give us the values for a, b, and c from the equation for the circle, and we then need to convert those into Cx hat, Cy hat, and r hat, which we do simply using the equations that we saw in the slides. And that's everything really for the first example. We then display the results, create a circle using the create circle function based on those results, and write that out to a CSV file, and that's the data that I use to do the plot. We then have our second test, which is basically exactly the same, but this is the test to demonstrate the sensitivity to an outlier. So in this case we define there we go, num points minus 1, so 99 points, and then we add 1 extra point here at 0, 0, so that's our outlier. The 99 points are around the circle, the outlier obviously isn't, and we write that out. That's all exactly the same then as the code that we just saw for the other test. Code QBLSQ circle, test code QBLSQ circle.cpp std C++17. Okay, and let's run our code and see what we get. Test code QBLSQ circle. Okay, so testing the basic circle, we're given Cx, Cy equals 10, 5 and r equals 3. We got the result there of 9.97, 5.08 and r of 2.983, which I think you'll agree pretty close to what we started with, so that's very good. And display the actual beta hat values there just in case anyone's interested. And then we come to the test with the single outlier point, so given the same initial conditions, but notice now we get 9.08 and 4.45 for our center point and 3.3 for our radius, so we can see immediately from here that this is a considerably less good fit than we had in the simple case, and of course that was much more obvious from the plot that I showed back in the slides earlier, and that is simply a result of the fact that the single outlier positioned at 0, 0 significantly distorts the result that we get from the technique, because, as I said back in the slides, this approach is very sensitive to outliers and is not really a recommended way of going about fitting a circle to a set of points in the general case. Now it can work, and actually the reason I've done it this way is because I want this code for a particular application, something else that I'm working on, and in that case the data will always be roughly formed around a circle anyway, and I can be really confident that there are not going to be any significant outliers, and if there are, they're actually going to be very easy to detect. So in that sort of situation, and that kind of situation that I'm dealing with, then using this method to fit a circle works perfectly well, and it's very fast. It's pretty computationally efficient. It's really quite a good way of going about it. As I say, though, in the more general case, not really the best way to do it. Interestingly, actually, if you Google for fitting a circle to a 2D set of points, you can find all sorts of stuff out there, and a lot of really very sophisticated algorithms that undoubtedly would work more robustly than this one in the general case. But there we go. Okay. And yeah, that's really everything that I wanted to show about the code. Okay, so there we go. That's really everything I wanted to talk about today. We've looked at how we can reformulate problems related to fitting a plane to a set of 3D points and fitting a circle to a set of two-dimensional points. And we can reformulate those problems into a way that makes them solvable using linear least squares. Particularly in the case of the circle, we also discussed the limitations of using this approach to solve that type of problem. As I said actually in the video when we were looking at the code, there really are situations where linear least squares is perfectly appropriate for fitting circles, and that's actually why I've developed code to do this, because I want to do that myself. But as long as you understand the caveats and the limitations, and you're sure that your problem is solvable given those caveats, then there's really nothing wrong with doing that. Anyway, as I say, that's really everything I wanted to talk about this week. So, just if you like this video, please do remember to hit that like button, and if you haven't yet subscribed to my channel, please consider doing so. Okay, so anyway, I really hope you've enjoyed this video. It's been a great deal of pleasure making it, and I really look forward to seeing you in the next one. Thank you very much for watching. Bye.